We have on a national panel, as was shown earlier, and I think the slides will be brought up shortly. We have Niki Werkheiser that's going to lead off for about 5 minutes. Niki is a Director of Technology Maturation, Stmd, followed by a vision statement presentation by the Stmd Chief Architect, Mark McDonald. And Jerry Sanders and Mark Hillburger are the Principal Technologists for the ISRU and the Excavation and Construction side. They are our primary points of contact. Our meaning mine and Athonu's for the ISU and EC side. So we are almost on schedule. Without further ado, Niki, if you're online, are you able to start off?
I am. Can you sound check real quick? Can you hear me?
Yes, we hear you loud and clear, and we see you as well. Okay, thank you very much.
Thank you. All right, we can go on to the next chart. Good morning, everyone. I am thrilled to be here today, and let's see, it's Andrea's flipping charts. We can go on to the next one. I may have a lag.
Christina, are you able to advance to the next slide?
Are you talking to me, Andrea?
No, I'm sorry, Niki. We have someone else sharing the slides, but hang on one sec. I'll pull them up and get it changed.
No problem.
Is it not sharing the Insured American Global Leadership?
It is showing the title slide right now.
Right. And then
it's okay, Christina. I'm going to take care of it.
Happens to the best of us.
There we go.
Thanks so much. No problem. Okay, good morning, everyone. I am absolutely thrilled to be here today, and even more so to have such a great turnout for this workshop. I'm really not going to take much of our time this morning. We have a really exciting lineup of speakers, and I'm eager to dive into the good stuff. But I do want to set the stage just a bit by sharing kind of a high-level overview of what the Lunar Surface Innovation Initiative is for those who may not be as familiar with it. So first, I'm going to talk a little bit about the Space Technology Mission Directorate, which we are in, and our mantra is Technology Drives Exploration. As you can see here, we have a broad range of technologies that we're developing really across the whole mission lifecycle, and they include up there in the top, you can see in the colors on that top row, space transportation, expanded access, sustainable living, and transformative missions and discoveries. So all of these technologies here really span the technology readiness levels. The Lunar Surface Innovation Initiative is not a program. We do span across all the STMD programs and work with other mission directorates as well as industry, other government agencies, and academia, which you'll hear me talk a lot about, and it's really why we're here today. But what we're focusing on today, of course, is there in that blue box, LSIC, and you'll see that there are several areas, and of course, we're going to particularly focus on ISRU, excavation and construction, but I will note that all of these are really cross-cutting and obviously have interdependencies, especially when it comes to things like surface power and advanced robotics and autonomy, as well as surviving extreme environments and having access to the areas that we need to get to. So if we go to the next slide, talk a little bit about the Lunar Surface Innovation Initiative. It was just established in 2019, shortly after Artemis, and really just for the objective of working across industry, academia, and government through a combination of in-house efforts and public-private partnerships so that we could make sure that we're developing the transformative technologies that we're going to need for lunar surface exploration. And the way that we do this really is to focus on formulating and integrating those technology maturation activities, like I mentioned, across the TRLs. Also, importantly, utilizing our early uncrewed lunar surface flight opportunities, such as the Commercial Lunar Payload Services, or CLPS. We really need that when doing tech maturation. We do as much as we can on the ground, but there are some things that we really need to test the system within the actual environment that is going to be operating, of course. And we need to do that pretty early on so that we can, of course, inform those systems and get that TRL developed and infused into missions and systems. And then, of course, we're here today growing the Lunar Surface Innovation Consortium. It was established just so that we could do exactly these sorts of things and have an open dialogue, not just meet a couple times a year, but to have these focus groups and these workshops where we do these kind of supply and demand or chicken and egg type of conversations and have that candid, open line of communication. And then very importantly, you'll hear throughout the theme of this of leveraging innovative collaborative approaches so that we can expedite those technology developments. And that's really been a key tenet since the inception of LSII. And so we want to establish those robust collaborations. And you'll hear me talk a little bit more about that as we go on. And at the bottom of the chart, you can again see those 6 LSI capability areas that we focus on. Our thoughts are if through LSII, we can develop what I call the basic infrastructure, which sometimes we refer to as kind of those pipes and roads for these capabilities, then I think we can truly start to open up a commercial market and reach sustainability on the moon. And so for NASA, we can also test out the core capabilities that we need on the moon as well as for Mars. So go to the next slide. So as we know, we're here today to kind of this joint discussion with ISRU and Excavation and Construction. I'll just say ISRU is obviously extremely important. It's just a real simple concept, right? We're going to be so far from home. We simply have to be able to use the local resources for our consumables and to live and operate. We all know that in 2009, it was discovered that there's a lot of water on the moon's poles. Even the most conservative estimates suggest millions of metric tons. And so this water and these other materials that we're talking about, the metals that we're going to focus on today, are really critical for these missions and for consumables as well as for humans and our systems and even propellants. And furthermore, much of this development, as I mentioned in the demonstration for ISRU capabilities, do feed forward to our needed Mars capabilities as well. So in space tech, we work to develop these needed technologies for collection, processing, storing, and use of the materials found on the moon. I'm going to leave it at that for now because Jerry Sanders will discuss all of this much more in detail. Those are just some of the highlights. And if we go to the next chart, excavation and construction. So I see excavation as really a bridge between ISRU and construction. It's required, of course, for drilling and digging into the regolith to extract resources, as well as to gather up that regolith material to be used for construction. It's construction using the moon's resources will really be needed to provide protection of the crew members, the hardware and electronics on the surfaces, and there's really kind of endless possibilities in terms of storage and habitats. And when you have kind of a thought of a mobile platform for excavation and construction. This is another area where we have a great deal of industry and university involvement. For both of these areas, we are leveraging and learning a lot from companies on Earth that do these things terrestrially. And we're working a great deal with universities to understand the regolith properties and even make regolith simulants that we can use to test the hardware on Earth as well. But as we know, there are major differences and challenges that we're working through too. For example, excavation technologies, they'll need to be lightweight, yet capable of digging in reduced gravity. And then the larger scale construction systems must be autonomous and equipped to work without astronauts' help. So for all of these systems, what I'll say, if I had to add something to one of my kind of keep me up at night lists, working reliably in these environments. So the maintainability and reliability, I think, is particularly challenging. And we even see that in the commercial terrestrial systems. So Mark Hillburger will share much more on this today. If we go to the next chart, and this will be my last chart, so as mentioned, we can dive in. But I did want to leave you with some of the various partnerships and collaboration highlights that have resulted in, at this point, around $200 million of awards just since 2020. I did mention earlier that LSI really leverages a broad range of Stmd programs and working with the other mission directorates. And so increasing those really meaningful collaborations, in my opinion, is what is pivotal for establishing a true value proposition for all of the stakeholders involved. We're really serious about accelerating that needed technology development. And in order to do that, I think we have to be pretty assertive about leveraging those innovative ways that we can work together and to really bring out the complementary but different strengths across government, industry, and academia. So as you can see on the chart, there's a broad range of different kind of platforms we use, everything from crowdsourcing, such as our Centennial Challenges, and we have a Honey, I Shrunk the Payload Challenge, many others. Tipping points and ACOs, announcement of collaborative opportunities, just hit the streets on February 11th. They are open now, so I encourage everyone to take a look at those. SBIRs, NIACs, and really just a range of space grants and other ways to collaborate and partner across that spectrum of stakeholders. And then very importantly, of course, this relationship that we have with APL here in establishing the LSIC, as well as the system integration role, where they can gather up your inputs, your feedback, the results of these type of workshops, as well as them having insight into NASA's plans and roadmaps, and really connect the dots and see where we can further leverage these sorts of collaborations. So that is it from me for now, and I will turn over to Mark McDonald, who is our Chief Architect in Space Tech.
Thank you, Nikki. Mic check, can everybody hear me?
Yes.
Awesome. Well, I'm going to go ahead and dive right in. Next chart, please. They asked me to talk today a little bit about NASA's vision relative to ISRU exploration construction on the surface of the moon. And as chief architect for Stmd, I'm going to describe to you my point of view on that and what I'm working with my counterparts across the agency. The way we see it for the moon is, going back to the moon is hard, and going to the South Pole is even harder. But we don't want an Apollo program again where we do half a dozen missions and stop. We want to go and we want to stay. And to really stay on the moon, if you look at the National Space Council's U.S. space priorities, you guys can find those online if you like. They were published December 1st by the Vice President. They speak a lot about creating a robust lunar economy. So with that, to meet that U.S. Space Council priority, what does a robust lunar economy look like? There are parts of it that are, the transportation system and the landing system, and NASA's pursuing those through the Eclipse program and the HLS program. But we really need to talk about an economy is based on goods and services, and how are we going to create an economy that is more than the transportation system to get there? And that's what this conference is all about. So if I were to articulate, my vision for this, I would talk about first a global lunar utilization strategy. We need to develop the technologies that not only enable us to succeed at the South Pole, but enable us to utilize the entire moon for scientific and industrial purposes, as well as the exploration of preparing us to go to Mars. So expanding infrastructure and the ability to do global utilization kind of changes your perspective, because if I'm just going to drop down in one location at the South Pole, I can drop some solar arrays and I've got my power. If I want to expand to global utilization, you start thinking in terms of global lunar power grids and how do you distribute power over much longer distances. If you start thinking of industrialization for a robust lunar economy, you start thinking about much higher power needs. And quite honestly, the reason you start thinking about those higher power needs is this conference. So in order to do extraction of metals, in order to do ISRU and construction, those are high power loads. So the precursor to this need is the power to service the technologies you're going to be talking today. So whenever I talk this topic, I talk power, ISRU, and excavation and construction all as one in order to get to the end point. ISRU is creating the commodities we need in order to create the structures and roads, in order to create the oxygen and the other materials that an economy can be based on. And there are services surrounded in transporting those goods and materials, and additional services related to human habitation, exploration, and things like that. Those are some of the quick components of a robust lunar economy. So on that economy, if you're only making use of it, 1 day a year or 30 days a year, you're not getting full value of your technology investments. We want to be able to enable continuous lunar human and robotic operations so that we can get full value out of that economy and the investments we make in it. That's the vision that I want to paint, is global lunar utilization that enables continuous lunar human and robotic operations. Now on that, the one word that's not on this chart that I noticed that I'll put on it the next time I use it is, yes, we're developing the technologies for those things, but achieving them is going to be an incremental process, all right? We're incrementally going to get there, all right? You're not going to get there in 1 second. I saw a question in the chat that I'll answer right away of who are the customers of this economy. The answer is first, NASA will always be a customer of this. We've got a lot to do on the moon for decades to come, so NASA will be a tenant, but NASA shouldn't be the only tenant. Our international partners are going to have use for this. There are a lot of countries that want to participate on the moon that may not have the resources to do all of this themselves, but can participate of customers as one of many customers on it. So there's a lot of international interest. The next is industry itself. In creating these lunar commodities, when you start moving forward, there's a lot of industrial interest on the moon beyond ours. And in our demand side of it today, I think you'll hear some of the customers of these things. But there's other customers for everything from tourism to science to other government usage and things like that. Next chart, please. So on this, as Niki started to discuss and I introduced in the last problem, it's very much a multifaceted problem. The lunar dust, well, all of these mechanisms to build the materials and process it have to be dust resistant. The reliability that Niki talked about. Even though the transportation costs are going down, getting hardware to the surface of the moon is always going to be expensive. And we need to make sure it lasts. We don't want to have to redeliver stuff. So reliability is going to be a key issue. Power and power distribution. The transportation of goods, the regolith you collect, all right? The processing and storage of that, the distribution of it, and then you can start, if you really want to go into the future, you can talk in terms of things like both surface depots of hydrogen and oxygen and launching those to cislunar depots for farther flung things. So with that, there's a lot of different facets. And it's not only these, what I'll say, endpoint technologies, it's the avionics and autonomy that drive these things. It's the communication systems for both surface comm and surface to orbital and orbit to earth comms to control them. It's the structural dynamics for lightweight materials. This little ecosystem we're talking of excavation, construction, and ISRU is literally draws on every technical discipline in order for it to succeed. So in these technology areas, I just want to stress that it's not just ISRU technologies or excavation and construction technologies. There's also going to be avionics, autonomy, structures and thermal and every other discipline out there that's going to need to be brought to bear in order to bring this vision to a reality. Next chart. So with this and talking about this vision, I think it would be helpful if NASA were to publish what our envisioned futures were so that you can see NASA's envisioned futures for ISRU and excavation and construction and all the different multifaceted disciplines that I talked about. So rather than teasing you, that's exactly what we're going to do. Each of NASA's technical discipline leads, our system capability leadership teams, and our principal technologists have created what we're calling an envisioned future priority package. It's a short PowerPoint presentation. They range from 10 to 15 pages long. And in that, we go through and describe our envisioned future in each of these areas. So, and with that, we also begin to discuss what are the priorities as we see them. Go ahead, next chart. And what our plan is we're actually going to publish these in an RFI coming up. And we are going to invite industry and other government agencies and even internationals to give us comments on these envisioned futures. The robust economy that I talked about, the end customer of that robust lunar economy is industry. So we need to make sure that our envisioned future embraces the future you want. So with that, we've got the Stmd strategic technology framework. It consists of these different strategic outcomes and capability areas. So you'll see in the next few months, we will be releasing the strategic outcome envision future priorities relative to the GO thrust. A few months later, We will release all the ones in the live thrust, which this community will be very interested in. So in the June to August timeframe, we'll release the Envision Future packages for both ISRU and excavation and construction. And we really invite this community to comment on them to see if our Envision Future is inclusive of yours. And hopefully you will see yourself in what our Envision Future is. But if you see comments for improvement where we might be able to do things smarter or more inclusively, that's the feedback we're asking for in this RFI. Following in the third, fourth quarter, we'll be doing the explore thrusts and the land thrusts to complete all of our packages. The reason we're phasing these out is, every one of these topics is a 10 to 20 page presentation. We didn't want to flood industry with, 200 pages of stuff all at once and say, please comment all at once. So we're stretching it out over a little bit of time. But our intention is to provide more depth to our communication with industry and share our strategic planning so that we as a team can produce the envisioned future we're all looking for. I believe that's my last chart. Is that correct? Next chart. So this is just the details of the NASA Strategic Technology Framework. And for every one of those bullets in the outcome, there will be an Envision Future package that we're going to be publishing. So with that, Jerry Sanders, my SCLT lead for ISRU, and Mark Hillburger, the Principal Technologist for Excavation and Construction, they're going to give you a little bit of a sneak peek of these Envision Futures, and they're going to present just one page of this portion and get it going forward and let you see what we're thinking. So thank you very much, and I look forward to the Q&A. Thanks.
Thank you, Mark. For once, I will probably be very brief if you go to the next chart. So as Mark was talking about, we're thinking much bigger now and much longer term strategy than we have in the past. And so this chart basically sets the stage for not just what we're doing right now, but where do we really want to go in the long term so that the things we do today get us there. So you start with the statement of wanting to have scalable ISRU production and utilization capabilities and what we call sustainable commodities for both the lunar and the Mars surface. And when I say commodities versus consumables, it starts to lend itself towards the idea that we're doing this for commercial reasons, not just for extending a NASA mission or such. And you start with the top left-hand corner, which is basically the water and the oxygen that you heard about Niki mentioning before, but now also bringing in other commodities, the metals and such, where we start with, first of all, making sure we know where all the resources are to a scale that will allow us to go to commercial mining operations. Initially, if, for early commercial customers, probably in the tens of metric tons of commodities, oxygen, water, hydrogen, whatever the case may be. But we recognize that we really need to think about scaling these up to hundreds, if not thousands of metric tons of product per year. And you see that in several of the commercial road mapping activities that have come out over the last several years. The other boxes start pointing specifically towards some of those other commodity users. The bottom left-hand side talks about the work that we're doing with Mark Hillberger and the construction and manufacturing and energy aspects that Mark McDonald mentioned, thinking about the power infrastructure, the construction and manufacturing infrastructure. Initially, things as simple as how do we provide the feedstock for just making a simple landing pad. Over time, that's probably hundreds, if not thousands of metric tons of regolith processing to be used in construction projects. Besides metals, we want to start thinking about plastics and other binders that we could be doing. And this should be able to lead to, hopefully, building that infrastructure that Mark mentioned in terms of energy generation and storage and transfer, as well as establishing the longer term goals of recycling, repurposing, and remanufacturing of materials and waste. On the top right hand side, you start seeing that besides just these the infrastructure aspect, we're also making sure that we cover the habitats and the foods and what we need to support that kind of growth, whether it's water or fertilizers, nitrogen products and such, as well as trying to consider how we make foods and what is needed to do that for long duration missions. And then on the bottom right are the things that basically cover the transportation nodes, whether it's to and from the moon, whether it's up and down from the lunar surface, or all across the lunar surface, hopping or driving. You know, what kind of commodities are needed for that? Typically 30 to 60 metric tons per lander, at times leading to hundreds, if not thousands of metric tons per year to support a cislunar economy or Mars transportation. So we're looking at ISRU in two factors. One is, how does ISRU help us get to the moon and operate and transport around and back? The other is, why are we going to the moon and how do we enable the infrastructure and the growth there? And so this is what our longer term view is. And with that, I'll bring my chart to a close.
All right. Good morning, everybody. It's Mark Hillburger. And let me first just say thank you all for attending this workshop, and thank you to LSIC for organizing. I'm really excited for this opportunity to present to you and also to listen to all the great many speakers that we have coming up this afternoon. So as been mentioned now, you know, we are putting together a longer term vision for creating permanent lunar settlement and a vibrant space economy, and the establishment of lunar infrastructure is critical, as you can imagine. Central to this is the ability to perform autonomous excavation, construction, and outfitting tasks for the creation of things like roads, landing pads, and habitable working and living spaces, as well as the emplacement of power and ISRU infrastructure, as they were just mentioning. And so with that in mind, I'm just going to spend a few minutes describing on my next chart, please, our vision for autonomous lunar excavation, construction, and outfitting. I'll refer to that as ECO because that's a mouthful. So in this slide, I've broken ECO into essentially 4 areas of emphasis, including excavation for ISRU and resource production, excavation for construction, construction and outfitting, and then the final step of providing a sustainable off-Earth living and working, which is essentially the industrialization and commercialization aspects. And so I'll just spend a few moments talking a little bit about each of these. So first, in the upper left, you can see excavation for ISRU-based resource production, very closely linked to what Jerry was just talking about. This capability is required to mine and deliver raw regolith materials to the ISRU processing facilities, from which ultimately we would like to see hundreds to thousands of metric tons of commodities produced per year. So then next would be excavation for construction. Has many of the same technical challenges as excavation for ISRU, but obviously a very different mission. This capability provides several functions needed to support construction activities, including site preparation, things such as rock clearing, grading, leveling, compacting of the surface, as well as trenching for utilities and such. And also, as was mentioned earlier, excavation for Regolith for the production of construction materials such as metals and binders. And again, very strong ties to Jerry Sanders and his ISRU team for the material processing aspects of that. Then in the center part of the slide, you see construction and outfitting. We see different infrastructure construction needs to achieve this overall vision, as I was mentioning earlier, including roads, landing pads, blast containment shields, as well as unpressurized shelters to provide surface asset and crew protection. And then finally, an evolution of these unpressurized shelters to pressurized structures and habitats. We expect that construction of these structures will require several different types of construction methods, from relatively simple bulk regolith manipulation for producing road beds and berms, and to structural assembly of truss-based towers and walls and arches, and then finally advanced technologies and techniques such as large-scale 3D printing using regolith-based feedstock. In addition to construction, we have to think about developing technologies that are needed to outfit these structures. And so outfitting for us is sort of something I'd say a little bit newer to us, and outfitting really is all about providing the necessary power, data, and ECLS infrastructure within the structures, essentially providing the rough end of cables, pipes, air ducts, and all the interfaces needed to install all the subsystems. And so once all that is sort of looked at and researched and developed and demonstrated, our ultimate goal really is to develop and demonstrate these technologies and capabilities through not only NASA internal projects, but also public-private partnerships, and to transfer this technology to industry so that they can establish an industrial scale commercial capability necessary to build the permanent lunar settlement and eventual lunar space economy. And so that pretty much does it for me, and I thank you for your attention.
Okay, Mark Hillburger, thank you for finishing up the presentations from NASA today. I just want to say thank you again to Niki, Mark McDonald, and Jerry for very interesting presentations. I encourage each of you to go on to the Q&A tool and start answering some questions. So the way, again, this works, follow up on what Andrea said, is after each set of talks, we just had our NASA talks, we'll have a panel. So we're going to transition to a panel that'll last for another 30 minutes. And I'll be the moderator for that panel, which people could ask questions via the Q&A tool, not the chat session, but the Q&A tool. And they can be answered live, and they can be answered by text, and we'll close them out as they're answered. And then I'll remain the moderator as we transition to the supply talks. And we have, I believe, 6 of them, if I remember correctly. All right. So first, I want to go ahead and take the opportunity. Oh, and I will read the talk. I'll read the questions to the panelists so that they don't, have to figure it out for themselves. And I'm going to try to summarize some questions into one, as difficult as that may be. And I think I'll start with Mark. Mark, you'd mentioned during your talk that we should focus on the very big picture, long-term sustained presence, continuous operations, global use, and you're releasing envision futures, in a staggered sense, go, land, and I forget, I'd have to look at what they are again. Related to all that, and you touched upon this in terms of the role of industry as customers, but can you expound a little bit more on the role of industry and also international partnerships in enabling these envisioned futures, not just as customers, but also as maybe technology providers and any other ways? After all, we are focused on industry. So could you comment more on the role of industry and international on our envisioned futures?
Sure, I'd be happy to.
Thank you.
So back early in the 1990s, I had the privilege of being the lead of the integrated architecture team that developed the space station. And the way we did that then is we had a true team that of international partners and industry that worked together to define what space station became. It wasn't a NASA team that went and designed space station. It was a collaboration of NASA, industry, and international partners that had discussions much like we're having here. I've been reading through the chat and the Q&A, and Harrison Schmidt, and a lot of the questions he's asking, those are exactly the right questions. What do we industry, what do we, the international partners, what do we, NASA, want to do here in order to have it satisfy all of our needs? The success in this is going to be an inclusive vision that has high participation. So with that, with industry, I expect industry to have some desires of what they want to accomplish on the moon for their own means, all right, that may require government funding or may not, all right? And our architecture needs to be inclusive of both of those cases. We need to support industry developing the systems and technologies such that they can be profitable on their own, all right? And we need to develop the systems and technologies such that NASA can accomplish its needs. I expect that, and I know that, we have a long list of international partners that want to both contribute in varying ways, and they want to utilize the moon in different ways. All right. So, and in our architecture, if we only have it to where international partnerships is only open to, very large countries with large budgets that can contribute large elements, that's obviously not the right answer. We need to have something to where small countries can participate at the level that they can afford to and desire to, and larger companies can do larger things. The same is true with countries and companies. There are, and it's one of those things, it's people tell me things in a proprietary means so that I can't necessarily answer them all in public forums like this. But there are several companies out there that have a desire to go to the moon independent of NASA and independent of government funding. And they may want to leverage our infrastructure and be part of a greater whole, but they have desires to go to the moon on their own dollar. So we need to be inclusive of those. Is the government, at this stage of operations, and you look at, low Earth orbit as an example, for the first, 50 years of low Earth orbit operations, the government was the sole customer for human spaceflight. But 50 years later, now we've got both SpaceX and Blue Origin doing commercial flights to low Earth orbit without government as the customer. So I expect that same evolution to happen here, but I also expect it to be dominant in government in the initial phases as well. So I hope that answers the question.
Mark, thank you. It more than answered the question, brought up some other questions as well. And I'll try it again. Combine some questions I'm seeing in the Q&A sessions, a lot of them. So feel free again for everybody to go in there. And just want to point out something Niki Werkheiser noticed. It's nice to have Jack Schmidt. If you guys have noticed, he's the Apollo 17 astronaut, walked on the moon, and only geologist scientist to do so. So it's nice to have Jack Schmidt attending. Thank you. All right, Niki, I think this question would be for you. Following on Mark's comments about investments internationally and global investments as well, as the Director of Technology Maturation and Stmd focused on domestic investment. So where do you see NASA making and investments? What do you see in terms of NASA making investments so that we can develop the technology to obtain these metals and oxygen and water from the surface of the moon? How can industry become more involved?
Yeah, so, obviously this is a really important question, right? Because we can have all the answers in this group, all the right technical answers, but we know that we have to be able to fund and support these activities, right? And have a plausible path. I always joke that dreaming of working for NASA since I was 7. You know, I went to my mom the other day and said, I never thought I'd be so excited about acquisition models. But the truth is we have to have ways to work together and ways to partner and collaborate that are meaningful. So I'll step back for a minute and just say, you know, people that know me know that my favorite quote is one from Henry Ford, where he said, if I'd asked people what they had wanted, they would have said faster horses. And the reason I think that's important and really applies to technology development is that it's really human nature to tend to start with a baseline of what we know, rather than to look at how we can truly disrupt the status quo with brand new or novel approaches. And so I think it's really critical that if we're going to evolve these technologies and have hopes of them becoming actual institutionalized capabilities, right, that can infuse into missions or commercial markets, that we can't get too immersed in groupthink or become overly prescriptive in requirements, or even get too married to singular development paths, right? So recognizing that this starts by establishing, you know, first, like we talked about, this ongoing dialogue within the community, because NASA all day long, if we're in an echo chamber, right, and we're putting out requirements, but we're not listening and having that feedback and all talking about, you know, what is state of the art, where can we push, where should we be leveraging true public-private partnerships more, then we wanted to establish this consortium, right? And as I mentioned, not only have those biannual meetings, but have these focus groups where every month across these 6 areas, we're diving down into technical discussions, talking about where are the real technology gaps, how do we start closing in on these gaps. We're listening to that. We're taking all of that in, and that is informing how we do our partnership and collaboration opportunities. So it's not just about talking and us putting information out there, it's about listening. And so listening to that feedback relative to those common areas and where those value propositions really are for those partnerships is the first step. I showed in that earlier chart that we have a lot of public-private partnerships and opportunities focused on industry developing technologies, but today I want to talk a little bit about the tipping points and the announcement of collaborative opportunities that are on the street today. They came out on Valentine's Day, and in the last round in 2020 of these tipping points, we selected over 370 million, I believe, in awards. And so for this cycle, we're implementing even some new ways of doing business. Number one, we've opened up our topics to be wide open. We have 2 major topics. One is Lunar and Lunar infrastructure. The other is in-space infrastructure and capabilities. That's it, wide open. And then through those opportunities, really our intent is to foster that development of the commercial space capabilities and benefit NASA missions. So when we look at what we're trying to do with the tipping points, we want to catalyze multiple domestic industry developed technologies that can lead to commercial goods and services in a market from which NASA and other customers, as Dr. Schmidt pointed out, can purchase them in the future. The important part about that I want to stress is when NASA is investing in these technologies, we're not doing so we can own the capability, right? We really do want to foster that capability so that we can be users on the other end. In that case, I think it's very important that the government kind of be that bookend for that development, meaning that we invest in the early technology development, and then on the back end, we're also one of the anchor users, anchor tenants for the capabilities that have been developed. And so we want to help lower the industry barriers to entry through NASA cost contributions. And then for the first time, too, I'll say these awards are going to be executed through funded Space Act agreements. And this was really done in an effort, I think it's taken 7 or 8 years to make this happen, we really want to do that to trade the level of oversight and insight and data rights in order to incentivize an increased pool of industry partners and available technology. So we're really excited to see what we get there. So that's one kind of very real way. There's a lot of different ways I could talk about, but in this short time, I wanted to focus on those opportunities that are out now. I will say we're having an industry forum. It's a virtual industry forum that will be held February 28th, so next Monday, I believe. And that can be found at the Stmd website or on Inspires. And then we'll do 2 phases of proposals, just a mini proposal that's due first. It's a short proposal that has a template in the call for proposals. That's due March 31st. And then we'll down select a set to be invited back for a final proposal that would be due in July. So that's just one way that we're trying to really grow and try different approaches and novel ways that we can work together to make these things happen.
Thank you, Nikki. Thank you for the answer. We've had a lot of questions in Q&A, which again, I'm going to try to combined into one. And this one I'm going to target to Jerry Sanders. There've been several questions, and we are equal opportunists here, so we can ask water questions, I suppose, because they are related also to resources. I'm going to broaden that one out. So water is a is going to be likely essential to any sustained presence, but then so will metals and so will oxygen extraction, right? So one question, Jerry, for you is, what's the broad strategy to finding, characterizing, collecting, and processing water, but also, the oxygen and the metals? And I'm sure we'll hear from this by the future speakers, but some comments on that. And then bigger picture, this may be from Mark McDonald. If this is a precious resource or rare resources, is there a strategy or approach to working collaboratively internationally on either the prospecting and or identifying where to mine, where to set up the bases in order to avoid conflict? So kind of 2 to 3 questions in there. First with Jerry.
Okay, so I'll start the first one. I'll answer the first one, maybe start the second one and turn it over to others. So the first one, where does water fit into the bigger strategy? I think it goes back to what Mark and Niki have been saying, and that is NASA's role is to enable industry to take leadership on a lot of what we're talking about, the infrastructure and the commodity productions and such. So our job is to basically pursue all the different pathways to some extent, to the extent to help make any of those pathways viable. So with respect to water, we recognize the benefits and the issues associated with, if I have water, great, I get oxygen, I get hydrogen, I get radiation shielding, I get a whole bunch of different things. But also recognize where that water is, what its concentration is, how difficult is it to get to the water from both a physical perspective as well as power. All that plays into the economics. So as I've typed in the chat to Harrison and others, really we're trying to understand the economics of each one of these pathways and how we could buy down the risk and enable the economics to occur. So water is a path. So for example, Prime 1 and Viper are the first missions along those paths to get us more ground truth as to where the water is and how difficult would it be to get. At the same time, we recognize that there's other commodities. Oxygen alone provides a significant benefit. And here again, besides the transportation aspects of water or oxygen, we want to pursue the metals and the other feedstocks that we could use for construction and manufacturing. Again, looking at holistically the bigger picture and how do we march both the supplier and the demand aspects going forward. With respect to data rights and resource rights and ownership rights picking locations on the moon, I think the Artemis Accords is the first step in that direction. I think there is ambiguity in the Outer Space Treaty that opens up the door. Several countries, the US, Luxembourg, Japan, have all signed laws stating that they will support, businesses in their own country. Obviously, that's not a long-term global solution to what needs to occur. But through those Artemis Accords, I think we can start discussing locations and how we do things, just like we do with geostationary orbit selections and communication wavelengths and things like that. So it definitely will need to be, in the end, it will be a UN activity. So those are my thoughts on those 2 questions.
Thanks, Jerry. Would anybody else like to comment on that? I'm not asking, I'm just asking, I'm not requesting.
I think Jerry did a great job on the answer, actually.
Yeah. Yeah, okay, great, fantastic. And we have plenty of time, we have 15 more minutes. And I think we should, another one has I'm going to try to combine some more questions in Q&A, and this one be for Mark Hillburger. And Mark, you had mentioned in your slides about the role of need for autonomous lunar excavation, construction, and outfitting. And from the questions, one I will come up with is, how does the ability of obtaining the metal from Regolith transform, how we might, or change the approach we might take to lunar construction versus the approach one would take if one had to bring all the material just from Earth itself? In other words, where should industry potentially focus itself in terms of what to build with in situ material versus bringing it from the Earth?
Yeah, that's a great question. I mean, I see the ability to obtain construction materials from lunar regolith as being truly, I hate to use it, but game changing. Because of the obvious reasons, not having to bring either prefabricated structures or even the pieces parts from Earth. And so, the immediate applications that come to my mind would be things like having essentially a hardware store full of building block structural elements, truss members, panels for structural assembly of towers, or blast walls and shelters, that sort of thing. Feedstock for welding, as well as 3D printing of components and spare parts. So, Niki talked a bit about reliability, but also there's the aspects of repairability, and wanting to have on-demand spare parts. So having feedstock for producing metallic spare parts, I think is going to be important. And then also supporting ISRU and power infrastructure. So having wire and components for power distribution and electrical systems and that sort of thing, I think is another big area that benefits. I think some of the earliest applications are going to be along the lines of cables for power distribution, as well as structural elements for the assembly of things like tall towers for positioning solar panels, and then eventually blast shields and shelters. And what's really exciting to me, and I think to others about this whole story, is that some of our early demos of autonomous construction, I see as, we'll bring everything that we need essentially from Earth so that we can, really sort of exercise that whole system approach of doing the assembly autonomously, doing the inspections, verifying that, these concepts work and that sort of thing. But now we also have an infusion path for in situ derived components that once that technology matures, we can then infuse those into the various infrastructural elements. And so I see that as being a really an exciting opportunity. So anyway, that's my quick answer on that. Thanks.
Thanks, Mark. Okay, we've had several more questions online, and again, I try to combine a couple of them. See, Jack Schmidt asked, is NASA, like China, considering the development of a very large rocket, Saturn class, or who knows, perhaps Starship class launch capability to support bringing this capability, these machines that will need to be used in order to extract the resources from the moon? How are these machines going to get there? And the ones that would then actually do all the digging and the construction and all. So maybe this question is for all of you. What is the path forward there? And related to that, what's the economic model?
I typed that into at least one of the answers. Yes, I mean, Starship obviously will play a factor into all of our ISRU and surface infrastructure discussions. And whatever capability we have to go to the lunar surface, and the cost per kilogram or the size will change the equation. So I remember when I first heard about the Red Dragon concept for going to Mars, and that SpaceX wanted to fly 2 missions per year, bringing 1,000 to 2,000 kilograms to the Mars surface every opportunity. That changed our complete perspective on what type of demonstrations and what type of hardware you would fly, and the level of certification that went with it. So I think as space transportation changes, and as capabilities change, we'll grow to that capability, and that will affect the economics.
I'll just add to that, saying for high mass delivery to the lunar surface, NASA has the LETS contract out right now, and the Appendix N contract that they're working on that includes HLS class cargo elements. There are multiple contractors that are proposing against those requirements for very high mass payloads to the lunar surface. So I expect there to be multiple offerings in that area.
All right, thank you both. Let's see, let's continue on. I'll probably go back to a question, Mark McDonald, probably for you again, but Laurent, related to Artemis Accords, to what extent do they enable the development of, the needed technologies and development of how was it put, to open up the acquisition source pool globally, since establishment of a lunar source economy will be a global enterprise? And to what extent with these accords could they be revised to better enable more collaboration? Thoughts on that?
I kind of hesitate on that. The speaker obviously has something special in mind, so I would say they're welcome to contact me via email with a specific consideration. I would say that the Artemis Accords enable a partnership framework to work together, and every country that I've spoken to has a specific use case in mind that supports their industry, their national visibility needs, their particular needs. And in all cases, the Office of International Relations in NASA and folks such as myself and my counterparts in the Exploration Systems Development Mission Directorate, we work to find something that meets those needs. So it's always a threading the needle of what a country wants to accomplish and what the architecture needs. So I'll use a successful example of recently. Australia is a signatory of the Artemis Accords. The Australian Space Agency wanted to find participation opportunities. The way they chose to do that is they ran several teams to look at areas of mutual interest. Through that process, NASA engaged them with subject matter experts from all of those different areas. And in the end, Australia, who is a world leader in autonomous excavation on Earth, chose to help develop a rover that would do small-scale ISRU excavation and bring that regolith to an ISRU payload. And Australia is contributing that on an Eclipse flight and sharing that data with NASA as part of their international collaboration in the Artemis mission. So you can see that Australia is getting their needs met, and working with industry that they're supporting within their own country, and it's contributing a vital part to our goals of furthering autonomous excavation, construction, and ISRU, and working towards getting that technology worldwide. So I think it's working. I don't know of anything in particular I would change in the Artemis Accords. I would say that it's working pretty well right now.
Great, thank you very much, Mark. We have about 5 minutes, and I think everyone has noticed I'm tending towards questions and compelling questions that are broader. But there are many focused questions in the Q&A which are directed to one or another principal technologist. So I'm not going to ask those questions, but I would ask you, Jerry or Mark Hillberger, to answer them as you've been doing continue to do so online so that those questions could get answered. I don't think this Q&A session continues on into the next panel. It may. I actually don't know. We can't count on it. All right, so next question. Yeah.
At the end of the day, if you have questions that are unanswered,
Yeah.
Send me a list of those and the email of the person asking it, and I will drop an email response to make sure people get their questions answered.
Thank you, Mark. I won't promise we'll send you the emails along with it, but we'll certainly send you the questions and we can post them on Confluence
That's fine.
for everybody
That's
to log
fine.
on to. Yeah.
But I do want to stress something. We've talked a lot about water, for example, and such. Again, the purpose of this particular workshop is to go beyond the things that we've discussed already. We've discussed water and oxygen and propellants in quite a few different forms. We've talked about our plans and such about how we're going to proceed with those. I think, again, I would like to reiterate the fact that we're trying to go beyond that and look at a more sustained surface infrastructure and activity, and how does metals and other commodities from the Regolith support that kind of an activity.
Very well said. Absolutely true. You're here. And on that note, we have time for at least one more question. I'll paraphrase Alex's question, which is the in-space manufacturing team had a vision to be eventually manufacture entire systems in space. So to what extent do you see the balance between launching infrastructure from the Earth versus building the materials or building the infrastructure there on the moon? So right now we have to launch everything from Earth because we don't have the capabilities, right, to make anything on the surface of the moon. We're figuring out what that is. This workshop is part of that. But where in the long term do you see this going? Do you see the moon as a completely self-sustained presence, except for maybe some food stuff? Or will the moon be continually dependent on resources from the Earth, for any sustained presence? And how do we get there? It's probably a Mark McDonald question again, taking advantage of your time since we have it. Niki?
I actually lost the thread on that. Can you summarize?
Sorry for meandering. What is the eventual goal for the amount of infrastructure material to be built on the moon versus the Earth in order to really obtain a sustained presence on the moon? Is there a metric or goal?
Okay, and the answer is, that's why I wanted to hear it again. The answer is, I at least don't think that way in terms of setting a goal or a metric along that. I think that initially, prior to the infrastructure being delivered, it's obviously going to be Earth sourced, and that's the right way to do it, in order to establish that foothold. I think that we have a lot of different technologies we need to prove out here. How are we going to get aluminum out of the regolith? How pure is it going to be? What can we do with it? I think there's going to be a process that we go through in determining what the state of the possible is. And as we're informed by that, our architecture and our plan needs to be such that we can adapt with that knowledge as we go. So as I look at it, I think I need a high TRL surefire way to succeed and to keep moving forward. And in parallel, I need to invest in some medium TRL and low TRL higher risk solutions that also move me down the road, but provide me greater payoff should they work out the way we intend them to. And then as we learn, we have to adapt and go. So in the long run, and do I expect, high intricacy life support filtering components to be built on the moon? No, the really high tech stuff I expect to be sourced from Earth. I expect to be cheaper to do that there, avionics, things like that. The bulk materials of walls and floors and structures and roads and, aluminum spare parts, trusses, beams, those things, do I see those being able to be constructed locally? Yes. There's a lot of gray area between those two. And I want to keep open-minded to industry evolving and that metric changing. It's kind of the best answer I can give you, but I don't think anybody has enough situational awareness knowledge right now to really give you an accurate answer.
Yeah, and this is
Thanks.
Nikki. I'll just add that this is part of that chicken and egg discussion, but what I would say is, it's not black and white, there's gray area. And it's exactly why I use the term infrastructure a lot of times in the near term versus sustainability. For me, it would be imperative that we really collectively focus. When I say collectively, I mean government, international industry, academia, to develop the technologies and capabilities that are required to really establish that core infrastructure. And when I say infrastructure, it's those 6 areas, right? We're all going to need power. We're all going to need access to certain places. We're all going to need mobility. We're going to have to survive the extreme environments, right? These are all things any of us that are stakeholders in this discussion have to be able to do. So the more we can work together in the next 5 years or so to establish that infrastructure, then I think we can start talking about moving on to true sustainability. I agree with Mark that not everything would be done through in-space manufacturing. We've been, trying to develop and increase those TRLs even on space station, demonstrations with metals and plastics and recycling and reuse. And I think we have to carry that on to the moon and to some of our, deep space missions, because I think for somewhere like Mars, we're going to have to do that, right? And the moon is where we need to prove that out. So to me, it's kind of a phased process, moving from infrastructure to sustainability. And I think we have to keep pushing ourselves in that direction. I don't think we'll ever be 100%, using in situ or that kind of thing. But I do think we can't also just wait and see what happens. I think we have to design it into our systems. A lot of times with in-space manufacturing, if you don't design the system to be modular so you can replace the parts that break most often, then it doesn't matter how great your additive manufacturing are, you won't be able to use them effectively during the mission. And we learned that with Eclipse. With Eclipse on space station, almost the exact opposite of what they predicted is the higher rate probable maintenance and failures happen. We see a lot of valves and things where we have, orbital replacement units. We have to fly up a whole big unit, because a valve or a seal broke. So, that starts in the design process, and it has to be a deliberate thought process early on. Good question. Thanks, Alex.
Nikki, thank you very much for your final thoughts. And on that note, I want to give an opportunity to Mark Hillberger and Jerry for any final thoughts as well before we move on to our our first panel from industry. And I want to take the opportunity to thank Niki, Mark McDonald, Mark Hillberger, and Jerry Sanders for their participation as well. But if you have some final thoughts, please, Mark or Jerry, do you have any final thoughts? And before we move on
just
to
quickly.
Just
quickly, one is, I think the vision that Mark and Niki talked about earlier is something worth pursuing. Over the last several years, NASA has funded a number of different technologies and efforts going forward. We have Prime 1 and Viper being on the books to go understand the water resources better. Now I see, instead of just, the oxygen and water pathway, we're really starting to think about what does it take to have a sustained presence and a sustained infrastructure, and how do you grow them. And so I think this discussion today is the first of many I hope to see on what, besides the water and the oxygen that we've talked about for years, can we really start pushing.
Yeah, and if I could make just a few closing comments as well. Thanks for all the questions, and thanks for the opportunity. So just a little bit more information on what we're doing right now in terms of excavation and construction. The APL is helping us conduct some initial focus studies to look at, where does it make sense to use ISRU produced materials for construction, both in the near term, but also what's the potential for the longer term technology developments and implementation, and what's the infusion strategy. So we are working on that with the help of APL, and that came up in one of the questions in the Q&A. It would also be extremely helpful as we're moving on with these preliminary trade studies to understand, as was mentioned very early here, what types of materials can we get? What's the expected purity and mechanical properties is obviously of particular interest. So we can start to sort of narrow the focus from a structures and implementation point of view, as well as a development timeline. How long is it going to take for us to develop these technologies to derive these in situ metals? So appreciate it. Thank you very much.
Mark, thank you again. Thank you. Thanks to all the panelists. I'll give you a virtual clap. It's been a great start to the workshop. And I am still on the hook to facilitate the next discussions that we'll have, and the next presentation that we'll have. There'll be a break